Emerging technologies in robotics, automation, and launch systems are poised to transform astronomy forever. We need to rethink what a space telescope even means. You've probably heard hot takes on how cheaper launch costs mean bigger space telescopes, or how AI will replace astronomers or autonomously discover new physics. But here's the thing, I think that they're all missing what's actually going to happen, and the truth is, it will be far more interesting. Let's start with robotics, because it is the topic that we hear the least about when it comes to space telescopes. The Hubble Space Telescope is a 35-year-old machine still working at the bleeding edge of modern astronomy, which is completely ridiculous. Hubble is like the Brian Johnson of telescopes, outliving all of its peers. As a point of comparison on this, the year after Hubble launched, NASA put up the Compton Gamma Ray Observatory into a very similar orbit. And it performed admirably for nearly a decade, but when a gyroscope failed in 1999, NASA made the difficult decision to deorbit it because another failure would have meant losing control entirely. Coincidentally, Hubble also suffered a similar gyro failure around the same time, but from here on out, the fate of these two telescopes diverged because Hubble could be repaired. NASA sent the Space Shuttle Discovery to replace Hubble's gyros, upgrade its computer, and install a new fine guidance sensor. Indeed, that mission was just one of 5 servicing missions, culminating in 2009 with the installation of Wide Field Camera 3, which is actually the same instrument we used to discover the exo-moon candidate Kepler 1625b-I. So servicing changes everything, because Hubble stopped being just a mission and started becoming something much more, a modular orbital platform, and that distinction matters enormously. Missions are designed to age and die, but platforms are designed to persist, evolve, and be upgraded. Once you can service a telescope, you're no longer launching a one-off experiment, you're building space infrastructure. Sadly, when NASA retired the Space Shuttle, it ended the era of human servicing for Hubble, and now it's limping around the Earth with a reduced gyro complement once again. Moreover, many of its instruments are actually now becoming a little bit obsolete. For example, the Space Telescope Imaging Spectrograph, or STIS, was designed in the early 1990s, and yet it's still up there 2.5 decades later. And since then, we've developed far superior spectrographs using integral field units and high dynamic range sensors. The new NASA administrator, Jared Isaacman, has long expressed interest in potentially servicing Hubble again, and if that happened, it could actually eclipse many of the technologies on board even James Webb. And speaking of Webb, unlike Hubble, it was never really designed to be serviced because, after all, it's 4 times further away from us than the moon is. It would be a very risky prospect for humans to go that far out just to repair a telescope. But this is exactly where robotics could change the game. And NASA has experimented with robotics before, perhaps most famously with Robonaut 2, a humanoid robot that lived on board the International Space Station from 2011 to 2018. It could hold tools and assist astronauts in various ways, but it was largely stationary and very constrained. It's a bit like asking your useless friend to come over and try to repair something. But consider that recently Boston Dynamics revealed their new Atlas fully electric robot that is stunningly agile, able to sit, walk, and run with ease, and it is now part of Hyundai's manufacturing line in Georgia. But it has to be said that dexterity and autonomy remain major challenges for these machines. For example, Tesla's Optimus bot is incredibly impressive, but it is still controlled remotely by human operators. But if we look ahead 10, 20 years, then these robots should be able to autonomously repair telescopes in deep space with no risk to human life. Indeed, NASA's next flagship telescope, the Habitable Worlds Observatory, will be designed from the ground up to allow robotic servicing. It then becomes a space platform where robots could periodically switch out modular instruments, test out experimental designs, and keep the technology at the bleeding edge of what's possible, leading to an essentially immortal observatory, one whose scientific relevance grows rather than decays with time. And so, with each consecutive space telescope, we start to build up a fleet of such immortals, vastly enlarging our cosmic view over time. Technological advancements like these are changing our society, but they're often a double-edged sword. And today's video sponsor, Incogni, can help protect you against some of those darker edges, threats like data brokers, skimmers, and bots. It's kind of crazy that there are now thousands of companies out there profiteering off harvesting your data and then selling it on without your permission. But the law does protect us. Each of us has the legal right to contact these companies and demand that they delete this information. Problem is, it would actually take hundreds of hours to practically do this. So this is where Incogni comes in. They scour the internet for your information and you can confirm or deny possible matches, and then they use the weight of the law to make sure that your information is deleted from these databases. And this is sensitive information. I'm talking home addresses, medical history, social security numbers, and much more. Incogni has a new killer feature called custom removals, which lets you copy and paste any links where you find your personal information online, and then they take care of the rest. So to fight back, use my exclusive link, incogni.com/coolworlds, to get 60% off by using my code coolworlds. Once again, head to incogni.com/coolworlds and use the code coolworlds for 60% off. Now back to the video. Okay, so robotics could clearly be transformative, but this all ties back to the launch vehicles at our disposal. And I have to say that I think that the biggest impact of cheaper launches isn't what most people say. I've spoken about the potential impact of SpaceX's Starship on astronomy before, but as many of you predicted in the comment section, it is behind schedule from what was promised. But it has completed multiple integrated flight tests at this point, including successful booster catch demonstrations. If SpaceX is moving slower than we'd hope though, there is some good news that Blue Origin is rapidly catching up with their New Glenn rocket, which has completed initial test flights and is targeting uncrewed lunar missions in the near future. And I'd be remiss not to mention that NASA have successfully tested their own comparably heavy space launch system, or SLS, back in November 2022, with crewed missions planned soon. However, SLS isn't really comparable to New Glenn or Starship in terms of cost. We are talking some 30 times more expensive per kilo launched. But if either of those private super heavies can deliver this promised level of cost reduction, and especially in Starship's case with this enormous payload volume, then telescope design changes overnight. Now yes, obviously you can launch one huge telescope this way, which is exactly what the Habitable Worlds Observatory plans to do, but I think that this misses the real advantage here. Current heavy launch systems can't touch the capabilities of what New Glenn and Starship are talking about, and so what that means is that engineers nowadays have to spend an inordinate amount of time, energy, and effort just trying to minimize the mass of their proposed space telescopes. For example, James Webb is actually much lighter than Hubble despite having a mirror 2.7 times larger. And we all remember how in order to fit inside its launch vehicle, it had to be folded up like origami and then unfolded in space with no second chances. But with super heavy launchers, a lot of that dissolves and we get to focus on reducing risk and complexity. There is less need for complex multi-segment mirrors like James Webb has. Instead, you could feasibly launch monolithic glass into space with something like Starship, the kind found in ground-based observatories across the world already. These new mass and volume capabilities also mean that we could afford to launch entire fleets of space telescopes, not just one-offs. And as we all know, it is much cheaper to build the 100th version of something rather than the first one. The Nautilus telescope concept proposes to exploit these economies of scale by launching dozens of inflatable telescopes into space using Starship. Now, to be clear, this isn't an interferometer. We can't fly these vehicles so precisely that we could reconstruct optical images using multiple telescopes, but they can coordinate to provide huge effective collecting areas on faint targets. At the end of the day, cheap launches favors boring engineering, and boring engineering wins every time. The final game-changing technology is, of course, you guessed it, AI. This is perhaps the most difficult to predict, being the most nascent of the three in many regards. A lot of the commentary that you'll see online these days about AI gets very hung up on how it will replace all of our jobs, but I guess I always have to question how that economically makes any sense. But at least for astronomy, I think there is a much more optimistic take in that it will serve as the glue for the two previous technologies that I talked about. You see, even at Webb's distance from the Earth, the light travel time of 5 seconds is a substantial barrier to remote controlling it. More crucially, the telescope can store up to 65 gigabytes of science data, which is downloaded daily during 2 4-hour contact periods with NASA's Deep Space Network. And what that means is that if something went wrong during science observations a few hours prior, the earliest we could know about it is long after they're finished. This lack of responsiveness is perhaps most damaging when it comes to an effect known as systematic noise. For those of you who saw my recent video about my team's use of Webb to look for exomoons, then you know exactly what I'm talking about. Thermal drift, pointing jitter, detector persistence effects, and more corrupt our data, and by the time that we are looking at the data here on Earth, it is far too late to fix it. So in the case of our exomoon program, for example, we actually have to wait now 2 years until our target can be observed again to propose an engineering solution to the systematic that plagued our data. But it doesn't have to be this way. Imagine if there was a scientific engineer on board the telescope, one who monitored the entire system continuously and could make changes in real time to mitigate any systematics. It could adjust the dither patterns, rotate the field, adjust exposures, or switch readout modes right there and then. That's something that no existing space telescope can do. Future space telescopes won't just collect data, they'll interpret it whilst it's being recorded, and they will modify their behavior accordingly. And this activity could span years. The telescope could learn how the detectors age, how to respond to tiny mirror deformations, and how the instruments vary with temperature. The telescope could then predict changes before they even happen. What I'm really describing here is a telescope which doesn't just observe the universe, it observes itself. With these technologies, space agencies across the world have an awesome opportunity to transform our view of the sky. AI clean data from fleets of Immortal space telescopes kept in mint condition by robotic astronauts. We could soon be moving into an era of continuous high-definition video of the entire sky in multiple wavelengths, colors, and polarizations. The opportunity is there for us to see our universe as we've never seen it before. We may even look back to today and be startled about how much we were ignorant of. Look, it's easy to extrapolate dystopian futures from emerging technology. Humans have been doing that for over a century already. But the future really is what we make it. It's our choice. We should never forget that. But the truth is that the future of astronomy isn't just dictated by physics, it's authored by budgets and priorities. And when people speak up for science, it matters. So yes, it might take a bit of work in order to keep the dream alive, but if the reward is the universe itself, then I'd call that a bargain. So until next time, stay thoughtful and stay curious.
It will orbit above our murky atmosphere and obtain images of objects that are incredible distances away, perhaps of galaxies 14 billion light years distant, so far away that when the light first set out towards us, there was no Earth, no Sun, no Milky Way galaxy. We will be probing the time of the earliest history of the universe.